So we talked about Kepler's 3 laws of planetary motion, and now we need to finish up with Newton's 3 laws of motion in general. So Newton's first law is an object in motion or an object at rest will stay in motion or at rest unless acted upon by an outside force. The other one was relating force and acceleration. F is equal to m times a. And then this last one says that for every force or action, there is an opposite and equal force or reaction. So the reason the space shuttle fits into that category is down here, you can kind of see that it's on its way out. Kind of this cloud here is an indication of combustion, burning, right? Okay. With combustion, basically you have a chemical reaction. And what this chemical reaction has done is created a force, a positive force outward from the Earth. So if I kind of put the Earth's surface down here, okay, we have a force, a crazy great force when you burn that hydrazine or whatever, going like that underneath the rocket, or yeah, the rocket that's carrying the space shuttle. And then what we do is we have an opposite and equal reactive force from the space shuttle down. Okay, so we have that one going up and that one going down, and they're equal and opposite. So it's that thrust actually using Newton's third law of motion to get it, to move it up. So kind of related to motion and objects in motion is this concept of momentum. So all objects in motion have a certain amount of momentum. So it's funny, like at the end of the day, you're like, oh, I totally lost my momentum. And basically, if you sit down, you stop moving, you have lost your momentum, because an object at rest has 0 momentum. But kind of related to momentum is, which would you rather be struck by? A person driving a bike at 15 miles per hour, or a Mack truck going down the road at 65 miles per hour. And you'd say the Mack truck don't want to be hit by because it's large and it's going fast, and you'd be right. So kind of the momentum that we feel upon collision is related to the mass of that object and how fast it's moving. Actually, not just how fast it's moving, but also what direction it's moving. It makes a difference. So momentum then also has what we call a vector or a direction to it. Momentum is mass times velocity. So we can actually associate with, I mentioned collision, okay, associate with collision. Collision, like if you were minding your own business, standing still, and got hit by the bicyclist, hopefully, not the truck. If you got hit by the bicyclist, you would move, okay? You'd go from a speed of 0 to some sort of speed that's not 0. You would accelerate. A force would act upon you to create that acceleration, okay? And in doing so, and we're going to talk more about kind of this conservation of everything, basically you became a system with the bicycle and its rider, and basically though the total momentum of that system needs to not be added to, needs to be what we call conserved. The energy of that system needs to be conserved and can be tracked. So in a minute I want to talk about something that is not straight momentum, like kind of the bicycle rider, or, you know, okay, that's straight momentum, the Mack truck driving down the road. There's this thing called angular momentum, and I know straight momentum can have other twists because it has that vector quantity with the direction with the velocity. But angular momentum has to do with objects that are orbiting, angular momentum, okay, associated with orbiting planets, and or with objects that are spinning, okay, rotating planets, okay, angular momentum. Okay, so I have a little slide kind of showing you that. So back to just straight momentum. This kind of reminds me, have you ever seen the Newton's cradle, where you basically have kind of rails and balls kind of hanging from a pair of rails? It looks kind of like V's, and these balls kind of hang and touch each other, and you take one ball, you lift it up, and it comes crashing and it hits the other balls, and what happens? This one kicks off, and then this one kicks off, and this one kicks off. They go like that sort of thing. Okay, what's happening is the moving object is imparting all of its momentum, because it stops, right, when it hits, imparting all of its momentum to actually the one that can move now on the other side. Okay, then it imparts its momentum here, and here, etc. Remember, momentum, like you see at the top here, can just kind of simply be calculated as taking mass of the object times how fast it's moving. So here we have a scenario where a red block is moving at 4 meters per second. It weighs 1 kilogram, and it's going to smack into the 2 kilogram block. Assuming the red block is going to stop, okay, kind of like the Newton's cradle, and transfer all of its momentum to the blue block. Can you see where 4 times 1 is a value actually of 4 kilogram meters per second? So when that 2 kilogram block takes off after the red one stopped, the product of the velocity times the mass has to also be equal to 4. So 2 times 2 is 4 again, and units would be kilogram meters per second. So this is like swapping momentum. So I mentioned angular momentum needs also to be conserved, and this doesn't have to do with momentum, but it has to do with forces. Remember, according to Newton's second law, anytime you see acceleration, there must be some force creating that acceleration. And I also mentioned that because planets orbit the sun not in a straight line, how would that work? But in a kind of circular-ish ellipse. The shape is an ellipse. But whether it's a direct circle or an ellipse, it's the trajectory of the planets keep changing. It keeps changing direction as it orbits. Okay, so there must be some acceleration going on here, and that's the force. Okay, what keeps a planet orbiting the sun? That would be the force of gravity. Okay, as summed up by the universal law of gravitation, m1, m2 divided by d squared. So I guess also related to that then, once we have inserted ourselves in orbit, or once our planet is established in an orbit about a sun or a star, our sun, that angular momentum needs to be conserved. Just like we saw that red block kiss that lighter blue block, it transferred all of its momentum. Momentum could be tracked, needed to be conserved. Okay, so when we talk about angular momentum, we throw in a term, not just the mass and not just the velocity, but also the radius of the motion. Okay, so the angular momentum needs to be conserved. I'll go ahead and put the word be conserved over here. And it is calculated by the mass of the object times the velocity of the object's motion times the radius. Okay, and a really good example of conservation of momentum is coming up. Okay, so remember, this angular momentum involves both orbiting and rotating objects. And the planets are doing both, right? So the conservation of angular momentum really kind of is displayed in a skater, as she has her arms out, okay, and she imparts a particular, uses a particular amount of energy to go ahead and impart a rotational speed, okay. Notice, let's see, do I have it down here? Yeah. Notice, oh, let me go back. P for previous, okay. If I were to ask you what happens when she draws her hands in, you already kind of see here, she's spinning faster and faster. And you probably already, I've seen this on TV, okay? So out, she's spinning this way. Bring her arms in, she spins faster and faster and faster. So here's how this goes. Basically, if angular momentum needs to remain constant, whatever she started out with, she needs to continue with, and her mass is constant. Okay, she hasn't gained weight or lost weight, right? And as her as her radius decreases, brings her arms in, okay, her velocity must increase in order to have the same, what we say, product, or the same result of multiplying those three terms together. If she were to go ahead and put her arms back out, okay? If she increases her radius, okay, then her velocity must decrease. Okay, this relationship, one going up, the other going down, or one going down, the other going up, we've run into actually in Chapter 4. This is what we call an inverse relationship. And here it happens because we need to conserve the amount of angular momentum we originally started out with.